Hello, this is Elizabeth Fisher, and in this presentation, I'm going to explain how to use tables to look up thermodynamic properties. To illustrate this, I will use a specific example related to ocean sequestration of CO2. Here's the motivation for the example that I will be using. You may have heard of carbon sequestration. One method of carbon sequestration that people have discussed is removing CO2 from power plant exhaust and pumping it deep into the ocean. If you were interested in implementing this idea, there are a lot of questions you would need to answer. For example, what impact would the CO2 have on marine life? How long would the CO2 stay in the ocean before getting into the atmosphere, etc.? We can't answer all of those questions, but we can answer a basic thermodynamics question. And here's the question. If you pump CO2 into the ocean, will it rise or will it fall? In other words, what is the density of CO2 relative to that of seawater? Here are the steps that I'm going to follow. First, I need to choose the values of temperature and pressure at which to evaluate the density of CO2. Second, I need to decide which phase of CO2 is present under those conditions. Third, I need to look up the value of density of CO2 under those conditions. And finally, I'd like to compare that density to the density of seawater. In this whole example, I'm going to simplify things by considering pure CO2 only and not taking into account other possibilities such as having the CO2 dissolve into the seawater. Let's start with the first step. Since I'm interested in evaluating a thermodynamic property of a simple compressible substance, I need to start by knowing two independent properties. I'm going to look up or calculate values of temperature and pressure at a particular depth in the ocean, and I'm going to assume that the CO2 will be at the same temperature and pressure as the ambient seawater at that depth. I'm going to do all these calculations at two different locations. The first one is the bottom of the North Sea, which is relatively shallow. Its average depth is 95 meters. I can estimate the pressure at the bottom of the North Sea by starting with the atmospheric pressure, that's the pressure at the top of the water, and then adding the pressure difference due to the weight of the column of water, which is rho GH. So if I do this calculation, I find that pressure is 1.06 times 10 to the 6th pascals, which is approximately 1 megapascal. I can also look up the temperature in the North Sea and find that it is approximately 280 Kelvin. So, now I know two thermodynamic properties, temperature and pressure, and I want to find the phase of CO2 that's present under those conditions. So we're on to step number 2. Now there actually are a couple of different ways to find what phase is present, and I'm going to show you two different ways. First, I'll use a phase diagram, and then I will use tables. So here's a phase diagram for CO2. It's a map in temperature and pressure coordinates, showing the regions where different phases are present. The solid phase is in red, the liquid phase or subcooled liquid, compressed liquid, is in dark blue, the gas phase or superheated vapor is in gray, and the supercritical fluid phase is in light blue. The black lines are regions where saturated liquid, saturated vapor, and saturated solid are present, and also where we have two-phase mixtures of saturated vapor and liquid, or saturated solid and liquid, or saturated solid and vapor. So, our job now is to find out where on this phase diagram we are when we're at the conditions at the bottom of the North Sea. Okay, so we know that the pressure at the bottom of the North Sea is 1 megapascal, which is the same thing as 10 bar. This doesn't really tell us what phase is present because all three phases, solid, liquid, and gas, can be present at 10 bar depending on what the temperature is. Okay, so we need a second thermodynamic property, and fortunately we know the temperature. So we need to be both on the horizontal line corresponding to 10 bar and on the vertical line corresponding to 280 Kelvin. So we must be at the intersection of those two lines, which is where I've now drawn a star. So we can see in the phase diagram that the CO2 injected to the bottom of the North Sea is going to be in the gas phase, and that's otherwise known as the superheated vapor phase. Now let's get the same information from tables of properties. We don't always have quantitative phase diagrams available, so we may need to look things up in tables instead. The back of your thermo textbook should have several tables of properties for different chemical compounds. It may not have properties for CO2, but it will have properties for steam and other materials. And they'll probably be in more or less the format that I'm using in this example. So the first thing to do is make sure that you have the tables for the right chemical compound, in our case CO2. Then you'll notice that there's several CO2 tables. A good starting point is one of the saturation tables. Okay, going back to the phase diagram, let me point out that the saturation tables are giving you the properties of CO2 along this line, which I have now shaded in green. The line represents saturated liquid, saturated vapor, and mixtures of saturated liquid and vapor. At any point along the saturation curve, saturated liquid is liquid that is just about to evaporate, and saturated vapor is vapor that is just about to condense. Ordinarily, there are two different versions of the saturation tables, a pressure table and a temperature table. This is the temperature table for saturated properties, which means that along the saturation line, we're choosing points that have nice round values of temperature, as you can see in this column, 220, 225, 230, etc. At each temperature, we have the corresponding saturation pressure, and then we have properties of saturated liquid with subscript F and saturated vapor with subscript G. Now let's focus on the line corresponding to the temperature at the bottom of the North Sea, 280 Kelvin. This line, which I've highlighted in blue, shows the properties of saturated CO2 at 280 K. From this line, let's read off the saturation pressure of CO2 at 280 Kelvin. Psat equals 4.16 megapascals. This is the pressure at which CO2 begins to evaporate or begins to condense if it is at 280 Kelvin. Okay. Now let's compare the actual pressure at the bottom of the North Sea to the saturation pressure at the bottom of the North Sea. The actual pressure is 1 megapascal, which is not equal to Psat. So we conclude that we do not have saturated liquid or vapor or a saturated vapor-liquid mixture if we put CO2 at the bottom of the North Sea. So what is the phase there? Well, the pressure is less than the saturation pressure, so we conclude that we do not have a high enough pressure to make condensation happen. So at the temperature at the bottom of the North Sea, we're not pressing down hard enough for condensation, and so we conclude that at 1 megapascal below Psat, we have superheated vapor phase CO2. We can see the same thing in the phase diagram. The purple star shows the saturation conditions at 280 Kelvin. We see that Psat is about 4 megapascals, or 40 bar. Our actual conditions are also on the 280 K line, but at a lower pressure, at the location of the gold star. We can see again on the phase diagram that we are in the gas phase, also known as superheated vapor phase. Okay, now we know the correct phase, and we're ready to go on to step number 3, which is finding the density. We couldn't skip directly to this step because at the start of the problem we didn't know which CO2 table to use. But now we know we're in the superheated vapor phase, so we need to find the superheated vapor table. Here it is. Superheated vapor table basically looks like a collection of smaller tables, each of which corresponds to a different value of pressure. Need to find the small table corresponding to the pressure of interest, which is 1 megapascal. And so it's this table on the lower half of this page. And now within that table, we need to find the line corresponding to our temperature of interest, which is 280 Kelvin. Here's that line highlighted in blue. So all the properties of the superheated vapor CO2 under the conditions of interest are listed in this line. Okay, we'd like to find the density, but it's not listed. However, we have the next best thing, which is the specific volume. And we can read off the value of specific volume, V equals 0.0495 meters cubed per kilogram. Okay, now we're on to our final step, which is comparing to seawater density. So first, we need to convert specific volume to density. Density is defined as 1 over specific volume. So the density of CO2 at the bottom of the North Sea is 1 over V, or 20.2 kilograms per meter cubed. This is much, much smaller than the density of seawater, which is 1025 kilograms per meter cubed. So we can conclude that if we inject CO2 to the bottom of the North Sea, CO2 will be in the vapor phase and CO2 bubbles will rise. Okay, now let's quickly go through a second case where we'll do calculations for a deeper ocean location. Let's say we want to inject the CO2 at a depth of 5,000 meters. The density at that depth is about 50 megapascals, the temperature is still about the same, 280 Kelvin. So what's the phase there? Let's look at the saturation tables again. We see as before that the saturation pressure at 280 Kelvin is 4.16 megapascals. At this location, our actual pressure is 50 megapascals, which is of course not equal to 4.16, so we do not have saturated liquid or vapor at the conditions of interest. Now this time, our actual pressure is higher than the saturation pressure at that temperature, so we conclude that we're pressing down on the CO2 with greater pressure than the value needed to condense vapor phase CO2. That means that we are in the compressed liquid, also known as subcooled liquid phase. Okay, so to look up properties, we need to find the subcooled liquid CO2 table. And here it is. And this table also is organized into subtables, just like the superheated vapor property table. So we find the subtable for 50 megapascals. Then we find the line for 280 Kelvin, and the value of V is 0.000921 meters cubed per kilogram. Okay, we convert that into a density. Density is 1 over V. It is 1085 kilograms per meter cubed. And we see that that's greater than the density of seawater. And so we conclude that if we inject the CO2 at 5,000 meters, we will have liquid CO2 and it will fall downward, and we may form a lake of CO2 at the bottom of the ocean.